here we go. We're going to talk about predicting redox reactions. We're going to continue on the next week. We're starting Friday. I didn't have you guys do any like redox specific things over the weekend because we didn't quite finish that. After that, we're going to do redox stoichimetry. So it's a lot of notes today, unfortunately. After that, though, we'll be kind of approaching the rest of the week, okay? Okay, I'm going to start here. Note to self on that. I think everybody's on Remind, which is nice. Thank you for that. Unit 2 test corrections, if you guys, for multiple choice specifically, I want to go over some of the mental math side of things. If I could do that during intervention today, I will. But if we can have those by Thursday that will kind of get them off your chest, and I'll give you guys time to ask me questions. Lab notebooks are due today, so I'll want those by the end of the day in my classroom, okay? So what we have to realize is that there's a lot of common reactions that are going to be including oxidizing agents that come up and up and up over and over again. So the ones I've highlighted are the ones that we should memorize how they are predicted to react. So if I'm an oxidizing agent, what am I doing? Oxidizing or reducing? Well, I'm an oxidizing agent, which means I cause oxidation to something else that I myself am what? Reduced, okay? So these are reduced. And if they are reduced, they gain electrons, right? So what we see is that there are some common ways that everything reacts. So in this case, everything I've highlighted here, including the entire list, they are actually in order of priority in how they react. So oxygen is like the best oxidizing agent because itself can go from an oxidation state of 0 to a -2 and be reduced quite easily. And that happens all the time. What kind of reactions use oxygen as a oxidizing agent? Combustion reactions all the time that will occur. So that might be something to think about when your redox in real life examples you guys are working with. All the halogens start off in their oxidation state of what? 0, and they can all form a maximum of a -1 charge or a -1 oxidation state. So we've never seen chlorine like -3, right? So don't try to reduce it so much. You're like, yeah, let's go down to -8. Go as far as you know you can because that's going to be its end state or its lowest state. Nitric acid comes in 2 varieties. Nitric acid can be concentrated form or diluted form. And what's kind of weird about nitric acid is it reacts with so many things, but sometimes it reacts differently with different things. So this one makes a brown nitrogen dioxide gas, and this one's not brown. I don't really think it has a color, but nitrogen monoxide gas is made from diluted nitric acid. So it'll just say concentrated or dilute, and you guys can use your prediction rules for a while, but we're going to try to wean ourselves off eventually. It's kind of up in the air on how much prediction you have to do on the end of your exam, so I try to give you what I can to make you survive the test, and then not ask you every single prediction. Like there might be 2 predictions on our test. It's very few, okay? Another one to look at, and this is the one we'll be actually doing a lab with on Thursday, is permanganate, which will come in the form of likely potassium permanganate. Potassium ion is usually a spectator ion because it's a soluble salt, would be at group 1. So permanganate, or they call this manganese dioxide. I know it's not prevalent, but we call it manganese dioxide quite often. Or how would you guys name that? Manganese what, JT? 4 oxide. So it's actually manganese 4 oxide, but they call it manganese dioxide quite often, inappropriately, but they do. But this right here is a beautiful purple color. So it's like one of my favorite compounds. It's beautiful. It goes through an oxidation state change to manganese 2 ion. And it will happen with either one of those, but this specifically is an acid, okay? So permanganate is purple. Permanganate is purple. Easy to remember that. And manganese itself is like a light pink color. So you can actually see it changing over time if it's ever, let's say, titrated. So we normally use what to tell us when a titration should end? Indicator, right? And what's the point of seeing, or what do we look for with the indicator? Color change, right? Well, what if we have a colored agent? We can't use necessarily an indicator because then the colors would blend, and we'd have Cassie's lab over again where they were mixing indicators. So what we would then look for is purple changing to pink, which would cause us to say, hey, this has met its equivalence point or something like that. So it can be used as a self indicator, which is a cool fact that permanganate can do, not many other things can do. So dichromate and chromate, the chromium ones, chromium polys, well, both in acid, and this is actually in acid form base, but mostly in acid here, will form chromium 3+. I skipped this one by accident, sorry. The purple permanganate again, in basic solutions, makes MnO2. You'll notice it says solid there. That is a kind of a black-brown powder. It's hard to see, but what you'll notice in solution, if you have a test tube of it, it'll kind of be like little flakes floating in solution. It won't be like precipitating to the bottom. It's not really heavy, but it's kind of a brown flaky. Looks like if you had a sunburn and you were flaking skin off. Fun fact. All right, so those are the ones that are common oxidizing agents. Remember, oxidizing agents mean that they are reduced. So all their oxidation states are going from a high oxidation state down to a lower one. All right, so I printed these for you, so you're kind of annotating on that for me, okay? Common reducing agents, so that means all of these are going to themselves be what? Oxidized. So if I'm oxidized, it specifically just means that my oxidation state is what? Going higher or lower? So if I'm oxidized, I'm losing electrons. So my oxidation state goes higher, right? It's going to get more positive. It's kind of counterintuitive. The ones that you've noticed and you've probably dealt with before a lot are the alkali metals, right? So the alkali metals themselves start off in that what oxidation state? Say again? No, just the alkali metals, these are solids. Are what? 0. Okay, it's a free element, and the free element itself will be oxidized to form a cation, right? So I can give you an example, like sodium going to sodium. Oops. I'm thinking of potassium. There you go. Sodium going to sodium 1 plus 1 electron. So that's like a half reaction involving a free element that's an alkali metal. All the other metals actually go to their highest oxidation state. And so generally you're like, oh, well, if I'm magnesium, what's my highest oxidation state? 2+. If I'm aluminum, what's my highest oxidation state? 3+. It's just the charge that they would naturally take on. But the weird ones, the transition metals, have many oxidation states. So who can tell me the highest oxidation state for copper? What are the only 2 charges you've ever mentioned for copper? 2+, or 1+ and 2+. That's it. Okay. So copper, the highest oxidation state is 2+. What are the 2 charges for iron? 2 and 3. So the highest oxidation state would be 3+. Highest oxidation state you've ever listed for tin. 4. Highest oxidation state you've ever listed for lead. 2+ is one of them, but it can go higher. Good job, guys. 4+. I think that's all of them I wanted to mention. Hold on. You can try copper, iron, lead. Yeah. Oh, and then manganese, Mn, can actually go up to 7+. That was something we talked about the other day in class, but it's not one you'll often see. So what basically, if you have a singular solid, a solid metal, or an ion, if it's in a lower oxidation state, it will go up to its highest oxidation state through oxidation. So I could have like copper 1 going to copper 2 in the case of ions going to ions for that specific example. Okay, so another thing that, well, hydrogen in the case of many reactions we'll see, hydrogen gas will go from an oxidation state of 0 to a +1, but it's mostly in the form of water, unless you have, of course, this in the presence of acid, and that's the only time we'll have an extra H+ freely floating around. Opposite of what we had before, right? Halide ions, meaning they're in their -1 oxidation state, will then be oxidized by losing electrons down to form their diatomic molecule. And what's its oxidation state over here for any of these? 0. So it's just the opposite of the first example. And then the other 2 I've highlighted are ones that we don't see terribly often, but you'll actually use 2 of those in our predictions we'll do shortly. Sulfates and sulfites, nitrates and nitrites are partners. The redox couples is sometimes how they're called. But basically sulfite will go to sulfate. We'll talk about how the oxidation state changes in a second. Nitrite will go to nitrate. And if you're ever trying to figure out, is it nitrate to nitrite or nitrite to nitrate, and you know it's oxidation, you just have to write the chart or the oxidation states in for yourself and figure out which way it should go. So let's go ahead and do that. Let's do the nitrite to nitrate example because I can have some space to write. What's the oxidation state of oxygen? -2. Nitrogen? Loud and proud. So this is a -1 charge, right? So 2 times -2 is -4. So it needs to be a +3 to keep that negative overall field. So that's a -3 oxidation state for nitrogen. This one is a -2 on this oxygen. It's still a -1 charge. plus 5. So it went from 3 plus to 5 plus, oxidized or reduced. By how many electrons? 2. So it's going higher in oxidation state. So you can always track that yourself. No, don't stress about that. The other ones we don't see quite as often, but the one I did want to talk about is the hydrogen peroxide. So in hydrogen peroxide, in the first set of examples, they are oxidizing agents. It produced one product. Look back to the very first set. What does hydrogen peroxide produce? H2O. Okay, so hydrogen peroxide produces H2O through oxidation or reduction? Reduction, right? Because it's an oxidizing agent. But look, it can also serve as a reducing agent. So it can do both, and it can do both at the same time. So the other product it makes is oxygen, according to this. So let's track the oxidation states and look for what's changing in oxidation state. What's the oxidation state? Actually, where do you guys want to start over here? You want to start oxygen or hydrogen? Some people are saying one or the other. So if I were to start with oxygen, what would I assign to it? What? Most of us are saying 2 minus, right? And then we kick ourselves because there's no way you can actually balance that out to be a neutral compound. This is peroxide. Remember that one exception? Oxygen, oxide is a 2 negative oxidation state. Peroxide had a -1. I don't know who said it, thank you. So this actually is a -1 because hydrogen can't be anything different really than a +1. So hydrogen is your priority, you send your +1 first. And so to offset that +2 overall, you need a -2 overall, which means that this has to be split as a -1. What's the oxidation state of oxygen here? 2 minus in here. Free element, diatomic molecule, is 0. So we actually have oxygen, and this is a +1, that's why I didn't note it's the same thing. We actually have oxygen doing 2 things. It's undergoing what here? Reduction, so it's going from a -1 to a -2, so it's being reduced here. It's a G. And it's going from here to here and being what? Oxidized. So I want you to note this one and call it a disproportionate redox reaction. So disproportionate redox reaction is that only when you have a single element undergoing both oxidation and reduction. That's it. So oxygen's kind of in the middle of its oxidation state world. It can be both oxidized and reduced. And so you generally would just have to say, like, what are the 2 oxidation states it forms? You may not even have to actually identify it as an disproportionate redox reaction. We just want to know, like, be aware of that because it'll come up and you're like, whoa, I've never done one like this. But now you have the idea that that can occur. So if you had this reaction and you had hydrogen peroxide decomposing to form water and oxygen gas, how could you test that to ensure it was actually breaking down to what we think it was? What's a test we could run? Flaming splint test, and what would occur with that? It would ignite, right? The flaming splint would be like kind of smoldering, and then it would ignite back in flame. All right, so the next set right here, and sorry, I'm going a little bit fast today. I got a little behind last week. These are just some examples of anhydrides. What do you think anhydrides means? Without water, okay? So these are examples of covalent compounds, which many times can either be gases or solids. I mean, there's a couple maybe that could be a liquid, but most of them are either gases or solids. So like carbon dioxide is a gas. Well, we can bubble that through water and we can hydrate it. So these acidic anhydrides, when they are added to water, they form acids. So I can sit here and say, okay, take this out of water, take this out of water, take this out of water, and we could do it. But we'd have to predict the acid that it would form. And here's your cheat sheet here. The acid that they form will have the same oxidation state as the anhydride. So what I mean by that is in carbon dioxide here in this first example, I'm not going to do all of them, I'm only going to do like 5 or 6 here. So this is how you predict the acid. You look at the oxidation state of the non-metal in the original form, and then we're going to predict what acid would form when it was added to water. So what's the oxidation state of carbon here? Plus 4, good, because this is a -2, so this has to be a plus 4. So we're going to have to form an acid with carbon having a +1 or +4 oxidation state. So you guys tell me, if I take carbon dioxide and add it to water, what acid is going to form likely? Carbonic acid, right? It's the only acid we dealt with carbon really in it. So let's look at carbonic acid. H2CO3, label your oxidation states. What's oxygen's oxidation state? 2 minus, what's hydrogen? +1, so we got a -2 times 3, it's a -6. +2, so it brings down to -4. So what does carbon have to be? +4. So that means that we predicted correctly. That's how we verify we predicted the acid correctly. Does that make sense? Let's do a couple more because I saw like 2 head nods, okay? So nitrogen or dinitrogen pentoxide. What's the oxidation state of this nitrogen here? Take a second and do that for me. What is it? 5+, okay, so this is a -2, so that's a -10 for the oxygens. So then with the 2 for the nitrogen total, each one has to be a 5+ overall. So what are some examples of acids with nitrogen that you've come across? Nitric acid, what else? Nitrous acid, and there's probably more, but we're going to form one of those. We just need to figure out which one it is. So look at nitric acid and nitrous acid, and let's figure out the oxidation state of nitrogen in both. Anybody got me? Nitric acid has a what oxidation state? +5. Okay, good, because that was a -2, so that's a -6, +1, it's -5, so that's a +5 overall. What's this one? So this is a -2, so it's a -4, +1, so what's this one? +3, okay. So that should be pretty fast now. We're probably getting really good at that. So if I were to add your nitrogen, or dinitrogen pentoxide to water, and you had to predict the acid made, you would predict that to be nitric acid, and then you'd have to balance per others with the 2. Yeah. So that would be your non-metal plus water yields acid. That would be the reaction. Let's do the last couple, okay? So I want you guys to predict the oxidation state of chlorine, phosphorus, and sulfur in these 3, and let's figure out what acids they would make. Anybody have a guess on the acid the dichlorine monoxide would make? Say it loud. Hydrochloric. So that is a true statement that the oxidation state stays the same. But what are the oxygens? Remember, it's got to have, hypo, I thought I heard hydro. Okay. Hypochlorous acid, which is what formula? HClO, so that's -2 + 1 + 1 for chlorine. Good, okay? It's the only one that one can make potentially, because the chlorous acid and perchlorous acid, they would all have, or perchloric acid would all have higher oxidation states for chlorine. Any guesses on, name this for me? Okay, tetraphosphorus digoxide. And then what's your acid of choice? I hear phosphoric, H3PO4. So -2 plus 1, that's a -8, -5, so it'd be a +5 overall for phosphorus. And then sulfur trioxide. Say again? I did not quite right here. Sulfuric. So that's that N part I really need here. So sulfuric, not sulfurous. Sulfuric. We have a -2 plus 1, and then overall, leaving us with a -6, we need a +6 on the sulfur. Okay? So those are acidic anhydrides, meaning that when they are added to water, all these nonmetals or nonmetal oxides would form acids. So we can predict it by just looking for the oxidation state to stay the same. All right, I'm going to move on to the last part of the notes from Friday. Okay, so let's skip this Friday because I didn't think it was important at the time. Okay, so we did that. We did this. We did that. All right, so this is the last part of the end of the other side of notes that we're working from, and these will be very familiar to you. Very familiar. So speaking of very familiar, look at number 2 down here. We just did this, right? We just covered almost that exclusively. So I'm going to scroll back up to that other part in a second. So we already knew that nonmetals and oxygen would synthesize. We knew that they would synthesize to form a nominal oxide in that case. So then we'll take this nominal oxide, which we call an acidic anhydride, right? So we're calling those nominal oxides acidic anhydrides. When we add them to water, they naturally produce acids. And so when we're trying to figure out the acid that we would then produce, it does depend on the oxidation state of the nonmetal, which is that process we just did like for a good 5 to 10 minutes now. So in this case, you guys could easily tell me, because we actually just ended on that example, for the sulfur trioxide, when we add it to water, which of these acids were made? Sulfuric acid, not sulfurous acid, and that's because it depended upon that sulfur's oxidation state. It was a +6 and a +6. All right, so that's your nominal oxide formation, addition of water. I just scrolled past this, but you guys tell me, if a metal oxide is added to water, what kind of things does it make? So metal what? When metal oxides are added to water. Metal hydroxides, right? So non-metal oxides make acids. Metal oxides make bases. So in both of these cases, oxygen is our oxidizing agent, O2. So the metal plus oxygen is going to synthesize, and we call this synthesis, but we could easily technically call it combustion of a metal, because oxygen is a combustion reactant in that case as well. So like we call this one a acidic anhydride, same thing. We're going to call this a basic anhydride, because when those are added to water, they would produce bases. And if those bases were strong bases, we would ionize them from the 2 metals that they produce. So the example for this one is, first of all, synthesis of magnesium oxide. Magnesium oxide plus water would yield magnesium hydroxide. And then what's a test we could run to double check that this was actually produced? Any test? Oh, I haven't got time for a titration. It's got to be fast. It was an easy peasy test I could test to see if I made a base. Litmus paper. Okay, the litmus paper comes in 2 colors, red litmus paper and blue litmus paper. What would the changes be if I were to test for those? Red to blue means that you have a base that's formed. Blue litmus paper would turn. Hold on. If it turns red, that means we're in acid. I'm going to do my Valley Girl in a second. Hold on. So, if you're in my class, you quickly remember that. It would stay blue. Okay, so red litmus paper would go to blue. That would mean it's a base being produced. And then blue litmus paper would stay blue because there was nothing impeding it to causing it to change. So, my jingle, if I can remember it, was, hold on. Blue to red, acid. Red to blue base. Okay, I tried to say like a Valley Girl. It's early. It didn't work out. But overall, litmus paper would change color. All right, last bit of prediction. Okay, these are combustion ones. Now, raise your hand if you've ever put a candle out at home. Or in general, maybe blew a candle out first day. You guys don't get out much, okay? What have you noticed? Like, if you've ever taken a candle lid and put it over the candle, what did you start to see with the flame? Come on, give me some details.
It would just so it would die off.
Okay, so it went out immediately. Like, that's the point I was putting the lid on. But what did you observe during that process? It's smoked, right? So what color was that smoke? Blackish, right? So who's ever, like, you know, put the lid on and taken the lid off and there's like all this black soot? Okay, so that's actually what we're doing here. I'm going to start from the bottom. So if we limit or severely limit the amount of oxygen that is being consumed in a combustion reaction, we actually change the products. So when we change the products, they look different. So one of the products we make in a severely deficient oxygen environment is actually just straight up carbon. Well, straight up carbon is soot. So that's kind of cool. Like, we actually can see that happening when we put a candle out. So the idea is that, oh, your candle is burning, and I'm using candles, but this could be any hydrocarbon whatsoever, or oxygen-containing hydrocarbon. When we have an excess of oxygen, it's happy, it's going to go ahead and produce carbon dioxide and water, like we've always stated a combustion reaction would do. So we call that complete combustion. And then if we have an incomplete combustion reaction, that's because we're limiting the oxygen a little bit, which can be quite bad, because what product is produced here? Carbon monoxide, which is, right, it's a silent killer, right, but it's toxic. So this is bad. We don't want that. That's bad too, but that's a different kind of bad. That's like greenhouse global warming. This is like, it'll kill you bad, okay? So it's incomplete combustion, which is why, what show did I watch? It's got Frank and Claire. Oh gosh. House of Cards, thank you. So, spoiler alert, when this guy died, he had his car in the garage, and he turned the car on. Well, it was producing carbon monoxide. Why do you think that was? Well, why was there a limited amount of oxygen in the garage? Because it was closed, and as the combustion engine was working, it was consuming all the oxygen, it started limiting it over time, which produced carbon monoxide. And so that would be incomplete combustion, which would be horrible. Then, if you just have severely, like totally eliminated most of the oxygen present, you're going to make soot, which is a black kind of powder. And that's what we see like with a candle. That, yet again, is still incomplete combustion. Anything that does not make carbon dioxide is considered incomplete combustion. What is the oxidation state of carbon in this one? 4 plus. What's the oxidation state of carbon here? 2 plus, and here? 0. So over these sequential reactions, you'll notice the oxidation state doesn't change quite as much. We'd have to actually do the hydrocarbon out to do the oxidation states for these. But we might do that in a second. But these examples with carbon could additionally be switched out for examples with sulfur. And so this is an example you should know. Whenever you make sulfur dioxide, that is actually what's in rain to make acid rain, which would then diminish the pH of the soil and cause like erosion of statues and stuff like that. So it's not like hydrochloric acid that's in the rain, it's sulfur dioxide gas. So what does sulfur dioxide gas with rain make? I hear two answers, sulfuric acid and sulfurous acid. Let's figure out which one it is, right? So I see sulfurous or sulfuric. What's the oxidation state of sulfur here? +4. Okay, what's the oxidation state of sulfur here? Say it. So -2 for the oxygen, +1 is -6, +2 is no, +4. Okay, what's the oxidation state here? Oh, I wrote that. Oh yeah, we did this one already, +6. Okay, so we would be making a weak acid overall. Like, this is sulfur that's produced from burning coal. It releases sulfur into the atmosphere. How can you limit the amount of sulfur that's within the atmosphere? Anybody know that? Took 8. Who knows this? Okay, well that's a shame. But sulfur is caused by combustion of coal. Sulfur can be put out into the world through smokestacks, but you can put scrubbers, which are sulfur scrubbers or carbon scrubbers, on the smokestacks themselves so that they actually react the sulfur away, so the sulfur itself doesn't go into the atmosphere. Because of course, when it's combined with water, it will make an acid which will degrade a lot of the plant life, animal life, and structures in the world. Okay. Sometimes they'll give you sometimes they'll give you scenarios set up like this, and they'll give you a paragraph of reading. It's about like environmental chemistry, and then you have to get to the details of like, okay, what do I have to do? So sometimes knowing like the background questions makes you at ease when you're reading them because you're not like, oh man, I'm finding all this new information and I don't know what to do. Okay, so I'm gonna go over this one later. I'm gonna go to stoichimetry. Oh, this right here. Okay, who's ever heard of ChemiBear in your research, in your advanced study evidence? Okay, well, ChemiBear is a really, really good site. It's got a lot of just nailed down details, and you might want to use that for any of your study evidence in the future. This is on my website, and it just has a lot of like prediction help and explanation help. I am not going through this right now, but I just want to let you know there are good things on my website for this unit if you wish to study those. Just a lot of really good examples. Disproportionate redox reactions is here. Some other tricks on how to predict oxidizing agents, things like that. Okay, so we're going to predict some products right now, and then I will stop. We'll take a break and we'll do stoichimetry. Okay, I normally wouldn't do all this in the same day, but I need time back. So look at the first reaction here. I'm going to add your notes in place because these will be good reaction predictions. And you got potassium permanganate, and you've got iron 2 fluoride. Looking at your predictions, your list of oxidizing agents and reducing agents, one thing that stands out to you is permanganate. The other one that stands out to you is probably chloride and the iron. But all three of those cannot be involved in redox. We can only have 2 of them. So look at your oxidizing or common oxidizing agents list. Okay, who has to be the oxidizing agent? Say again. Look at your common oxidizing agent list. Do you see chloride as an oxidizing agent? Yea or nay? No, you see chlorine gas. We don't have chlorine gas, right? Okay, so going down the list, who's next? Permanganate. We have to allow permanganate to do the to serve as an oxidizing agent. So write your half reaction with permanganate. Notice I'm canceling out the spectator. If you ever have a spectator, just get rid of it at the beginning because it'll eliminate your frustration. So permanganate in acid, notice it says in acid, has to produce what? Look at your list for now. Manganese 2. All right, so that's our first half reaction. We just predicted that permanganate from Mn2+. Now, look at your reducing agent list, so your common reducing agents, and we see iron 2+ here and chlorine 1- here, technically because it's an aqueous solution and those will be soluble. So as you're looking, who's at the top of your reducing agent list? Alkali metals, right? Do we have an alkali metal? No, so go to the next one. Other metals, do we have an other metal? Do we? Yes, okay. So notice it says on your list, does it say most metals and other metallic ions? So we have a metallic ion, so we're good to go. So let's look at our iron. It's going from a 2+, and it has to go to its highest oxidation state, which would be 3+. So we have successfully predicted our products. Now we must balance like we did last week. So our permanganate went to manganese. Our iron 2 goes to iron 3. Notice that we've canceled potassium out as a spectator, and chlorine is going to be a spectator too, so it's going to end up not being important for balancing. But now I need to go ahead and balance an acid. First step on half reaction number 1. Can you give me some steps here? How many? 4 H2Os, okay? So that gives me my 4 oxygens. Now I need what? How many? 8 hydrogen ions to balance out the H's. And then keep going. How many electrons do I need? I need 5 electrons on the reactants or products? Reactant. So I have 8+ and a 1-, so that's a 7+ oxidation state over here, and then a 2+ over here. So 7+ going down to 2+, I need to add 5 electrons to this side. So I'm going to add 5 electrons to the reactants. First half reaction has been balanced. Next one. Where do I add my 1 electron? Okay, so the 1 on the other products, and that's good for the oxidation state balances there. And then I need to balance my electrons, so what do I need? Multiply the bottom by what? 5. And then what? Add them up. So add those up, and then you guys are going to tell me what you have left. This one's wasn't too bad. H pluses, 1 permanganate, 5 iron 2s, yielding 5 iron 3s, a manganese ion, 2+ ion, and 4 waters. Check, check. All right, now let's try the next one. You guys tell me your thought process. Get me started, Taz. Okay, so let's look at silver. Silver, we have hydrogen ion and we have nitrate ion. Basically, those are the 3 things involved in this reaction. So silver is on our oxidizing agent or reducing agent, so Taz. Reducing agents, right? So silver solid is going to have to be reduced. I mean, it's going to have to be oxidized. So it's going to have to go to what? 1, right? So silver's highest oxidation state is a 1+. Like, I don't know if you saw in my summer packet, but I was like, occasionally it can be a 2+, but we never, ever see that, so we just ignore that, okay? So silver has to be forming a 1+. So I'm going to go ahead, I'm just writing my products up here, but I'm going to write my half reactions down here to kind of get me started. Okay? And then nitric acid dilute was in our top half, so our common oxidizing agents, meaning it's reduced. What does it produce? So nitrogen what? Monoxide. So NO3 dilute made, nitrogen monoxide. So then you guys go ahead and balance these half reactions, noticing that it doesn't say in acid, right? Doesn't say that, but it's in acid, right? Because it is in acid. So though it doesn't say, oh, balance this in acid, it is in acid. So you actually already have extra H+ ions in presence in solution. Okay, so do your half reactions and balance them. You got your, all right, there's one thing I want to note here, and I didn't do this up front, but I think you guys should notice this. You have a strong acid, right? So how does it exist in solution? Well, it's aqueous, so in that state of aqueous and strong acid, what do we see in solution? 2 ions, right? H+ and nitrate. So technically I should not write this like this. I should write it as H+ and nitrate, right? So instead of writing this, I'm going to write that as H+ and nitrate, but then how does that modify my reaction? 4 H+, right? Just because I'm taking one of those H+ off and I'm adding it to the coefficient I have here, and then nitrate. Doesn't change my charge balance, it doesn't change my matter atoms balance, it's just recognizing the state of the fact that it's a strong acid. Okie dokie? Alright, attempt the next one. And maybe before you start doing AP style, go back and just predict what that would form. Like you and honors can. Predict what that would form. What are you guys predicting would form? Copper what? 2 oxide, right? So it's copper oxide, solid metal, making copper a wet charge. So, not a trick question. You guys just said copper 2 oxide, right? So what's copper's charge here? 2. What's oxidation state here? Oxidation state. 2 negative. So if you did not have that ability to predict, you could have done the same thing though, because oxygen is a really, really great oxidizing agent, and it's going to go from 0 to what? -2. That's the first thing on your priority list. Copper is a other metal, right? Solid other metal, has to go to its highest oxidation state, which is copper 2. So either way, AP style or hey, I'm an honors chem and I can predict the synthesis reaction, you get the same answer. So don't think too hard on this. So this was a positive 2, this was a -2. If you were to write your half reactions, we can write that as, actually, do we really need to write our half reactions? Can we balance this? Okay, where do I need to balance? 2 in front of copper 2 oxide and 2 in front of copper. Okay, then let's track oxidation state changes to make sure electrons are balanced out. So oxygen, 0, 0. So oxygen's going from 0 to -2. And how many electrons are exchanged here? 2 for each of the oxygens. So overall, 4 electrons, because each oxygen is going to be exchanging 2 electrons. So there's 4 electrons total gained. This is going to go back to our oxidation state change balancing. And then copper goes from copper to 2+, but there's 2 coppers, so that's a total net of what? 4 electrons once again. Charge balance and oxidation state balance. All right, stand up, take a quick break. I probably need some minutes. Okay. All right, I want you guys to predict these. Stand up and predict these. Stand up and predict these. Or sit down and predict those, whatever you want to do. Christmas break, what? No. I'm going to change it a little teeny bit this year. It's like October. Just, no, because they have to have a little bit of sanity or something. Alright, so hold on. Can't talk to you. Last, so 25. Takes me.
I mean, that's good that you graduated last year and it's like 32%.
Yeah. Hold on, it's 14. I'm trying not to talk to you. Oh my goodness. Guys, this one's a long one. I'm sure you realize that. I'm just pulling everything down that I can cancel the end versus canceling in the middle. Okay. Oh, dang it. Sorry. Oh, 14 waters. Oh no. I would blame Alvin, but that would be mean. So 14H pluses is actually 14 water. Just deal with me. Just hold on. I make 11 hydroxides and 17, 9. Should leave me with 8. 8 water serum. Say again? Over here? Like at the bottom. Yeah. Hold on. So I just canceled out. So that would leave me with 8 over here. Alright, Alvin, go sit in the back for me. That is a 6, Darcy. Thank you. Right. I'm fixing my. I didn't balance in base at first, so I had to go back. And then. Alright guys, come back to me. So overall, you guys might be finalizing mid-step or, revising as you go because you forgot to add, balance and base 2 and you had to go back because you were talking and off task. Sorry, that was me. But overall, you should have 3 nitrites, I should add 4 waters. When I balance this the first time, I have 4 waters. Hold on. That's 9, 14, 17. Oh, this is 6 waters because 3 times this is 6. Okay, so this is good. So this should be 4 waters. Dichromate, 3 nitrates, 2 chromium, 3 pluses, and 8 hydroxides. Give me a head nod. Did you guys get this final with 4 waters? All right, with the 4 waters here instead. All right. So who was able to? I know it's messy. Bases just get messy in general. Were you guys able to follow through with your base in the first one? Okay. So do I need to do this whole thing again? Okay. Okay. If you can continue. 1 second. If you can continue, I just need some more space. Let me scroll down a second. If you can continue, what I want you guys to continue on just for the moment is this 10 reaction prediction. Find this in your packet for a second. I have 6 right here, but there's 10. If you don't need me, if you know how to do that first one, I'm just going to redo that first one real fast. And then I'm going to move on to REDOX stoichimetry because we got 25 minutes left in class, okay? So find this. It says AP chemistry practice with denies and predicting products with REDOX. Because I was going to try to do that. Let me do this part again, okay? Did you guys find this? Alright, for the moment, just predict the products, take your actual reactants, do what it says, predict those products for a moment. I'll rebalance this a little bit easier. It just might take me a second to do that. And then we have to move on to stoichimetry today. Okay, did you guys find that? Yeah, what was your question? You'll say in base, yeah. Say again? I'm going to multiply by 3. I'm just making sure I'm actually following through that coefficient. Yeah, are you making a... I get 10 I got 4 left. So if that's the nominal... Alright, this is the answer. I'm going to leave that up there for now. But go ahead and predict a couple more. Ask me questions and we gotta move on. Predict a couple more.
Oh, yes, not.
All right. Quick, hand yourself. 3, 2, 1. Non-metal oxides plus water yield. Non-metal oxide. Anything that's a non-metal with oxygen plus water yields acid. Okay? And the acid has to contain, well, oxygen and hydrogen, but the non-metal has to contain the same oxidation state we previously did. So, Megan, it's a combination of we're using the list of oxidizing agents, reducing agents, and then next natural prediction from an prediction. No. But if you look at a non-metal oxide plus water, you've got to make that mind out. We've seen that for 3 weeks, I think. The first 6 here, non-metal oxides plus water, combustion. First 3 would be the manganese. It doesn't say just do normal. Alright, let's make sure we can predict, and then we're going to move on to the straight. Oh, yeah.
Water.
Alright, let's finish the last one you're working on. I want to at least get 1 or 2 Stoic problems in, okay? Finish the last one you're working on for now. We can talk more. Yes. All right, come back to me. 3, 2, 1. Quick question, Megan, and I gotta move on. Shh. Marcus, Creed, I'll come back to me. Okay. Assign -2 to oxygen for within a compound. By itself, it's a free element. So O2 exchange totally. Let me do that during intervention. Okay. So I want to make sure you guys can predict first, and then after that we can go back. Okay. So come back up to me. Marcus, turn around, honey. Earth to Marcus. Thank you. All right. So we're going to take this reaction, and I know this is like REDOX. You can tell it's a titration, but let's take the reaction, predict together, and we'll walk through the whole process of stoichiometry together. Okay. So blah blah blah, iron 2 sulfate, blah blah blah, potassium dichromate. Right. So those are our 2 reactants, and then we'll figure out the question side of things in a second. So first step, we have our 2 reactants: iron 2 sulfate and sodium dichromate. Right. Which of these species, meaning the ions, do we want to say is in our redox reaction? You know for sure who. Okay, so you guys think iron, right? Let's look at our, what's the first one you guys have? Reducing agents or oxidizing agents? Oxidizing agents. Who's a common oxidizing agent? Dichromate, right? Dichromate for sure is actually really strong. It's a very, very common one. Oxidizing agent. So write down that as your half reaction. It's going to produce what? Cr3 plus. Notice this did say an acidic solution, so that's how it will be phrased. It'll tell you the solution type. So we've got this one, and we've probably already assumed who's going to be a spectator here. The sodium ion. Okay. So now our choice is between sulfate and iron. Who's higher on our list of common reducing agents? Iron. So iron 2 has to go to what? Iron 2 has to go to what? Iron 3. So who else is the other spectator? Sulfate. Okay, so we have our 2 half reactions, and I'll just balance them out. So chromium, what do I add here? A 2. And then next up, 7 waters. And then 14 H pluses. We've done this in recent history. And then charge balance. Yep, because this is a 12 plus overall, this is a 6 plus overall, so 12 plus needs to go down by 6 electrons to get me to 6 plus iron. 1 electron, because it's being oxidized. That looks like a 6, but that is a 1. 1 electron. And then coefficients, what I need? So multiply the top one or bottom one by 6. All right, so this is the part where I told you, normally in stoichiometry problems, you just kind of write your reaction out, but, or titration questions. This is I have to predict my products first, and then I have to balance it out. All right, so I know the 6 electrons are gone, so we have 14 H pluses plus dichromate. Keep wanting to write oxalate. 6 iron, 2 pluses yield 6 iron, 3 pluses, 2 chromium ions, and 7 waters. We good here? Okay. So now we have our BCE. So basically now we know how the reaction occurs. We know the ratio in which atoms or ions are added together to produce some sort of product. So now let's go back and read this question. What volume of 0.2 molar iron 2 sulfate is needed to completely reduce 50.0 mils of 0.4 molar sodium dichromate in acidic solution? Whew, right, so it's a lot of information. But with this, a typical stoichiometry or typical titration question, what do we always start with? So you're given who's your known, so who's our known? Okay, sodium dichromate. So if I were to start, what would I be mathematically doing? So taking the molarity in the liters to moles or millimoles, whichever you prefer. Okay, let's just talk this through first, then we can go. So once we get to moles of sodium dichromate, internal mole ratio just to get to dichromate, sorry, just to get to dichromate, it's a 1-to-1, so it won't really mess up your math. But now we're in moles of dichromate, and then what? Say again? Moles to iron, so moles of dichromate to moles of iron, what's that ratio? All right, so there's 6 irons for every 1 dichromate. Okay, so then we get to 6, or whatever, number of moles of iron 2. So go back to moles of the whole shebang, right? The iron 2 sulfate, and then what? How to use the molarity in stoichiometry? Do I want to multiply by 0.2 to get volume, or invert the molarity? Invert it so volume's on top, because volume is what I'm looking for. Okay, so that's just our normal stoic. It's just starting off with a redox style instead. So let's work through this. Yeah. Internal mole ratio? Is this in terms of iron? There's 1 iron in 1, so it's a 1-to-1 again. All right, so here we go. I'm going to stick with millis, I think. So 50.0 milliliters times 0.4 millimoles of sodium dichromate, and I'm writing everything else, so this might take me just a second. You guys like to abbreviate, and sometimes I don't know what that means. Okay. After you get to millimoles of iron or of sodium dichromate, you guys said do internal ratio. 1 millimole of sodium dichromate is 1 millimole of dichromate ion. I'm only going to ion because that's where we have expressed in our NIE. And then what's this next step? Go to iron, so 1 millimole of dichromate to 6 millimoles of iron, 2 plus. And then get me from iron 2 plus to what? The iron 2 sulfate. So internal mole ratio between iron and iron 2 sulfate is just a 1-to-1. So 1 millimole of iron 2 for every 1 millimole of iron 2 sulfate. And then next up, what was the molarity? 0.2. So how to incorporate that here? 1 milliliter on top and 0.200 iron 2 sulfate on bottom. That's millimoles, by the way. All right, math. Ooh, let's estimate. Yeah, let's estimate. All right, so here we go. 50 times 0.4. Think of it like this. Okay, hold on. 50 times, what's 0.4 as a percent? 40%, right? Or that's 4 over 10. Some of us need fractions. So what's 50 times 4? 200. What's 200 divided by 10? 20. Okay, so 20 is where we are now. So 20 times 1, no joke, no, that's fine. 20 times 6 is 120. Okay, divided by 0.2. So here's how we divide by 0.2. What is 0.2 as a fraction? What's 0.2 as a fraction if you just had to do it as simple as you could? 2 over 10, right? 0.2 is 2 tenths. So if I have 120, that's technically like 120 over 1, correct? I'm going to divide by 2 tenths. Divide by 2 tenths. This is copy dot floppy, right? So, or multiply by the tops and the middles, and then you're good. Whatever you guys call it, it works. What's 120? We need some space here. Times 10 over 2, right? Is that basically what you're doing? Okay, so ignore this on the bottom. What's 120 times 10? Okay, 1200. Or what's 120 divided by 2? 60 times 10. 600? I think it's 60 is the answer. Did we mess up someplace? But I think it's 60 No, it is 600. It is 600. Sorry, I remember I got this one in my head. So the answer is 600 milliliters. So 120 divided by 2 is 60 times 10 is 600. Math, right? Fractions will help you. So the answer is 600 milliliters. How many stick figs do I need? 3. So 600 milliliters of iron 2 sulfate. All right, so let's make sense of this and make sure this logistically makes sense. I need a ratio of 6 to 1 or 1 to 6 for the dichromate to the iron. So I used 50 milliliters of the first guy. So 6 times 50 should be what? 300, right? But I've got 600. So why is it 600, not 300? Because what? Because the molarity is it what? How different? Half, right? So if the molarity were exactly the same as 0.4, I would need exactly 6 times as much. So I would need 300 milliliters. But because the molarity of the iron sample is half of that, that's why I require 600, because I need more of it to react with me, or double it to react with the dichromate species. So that should make sense logistically, mathematically, and conceptually. Thumbs up if I can move on. Okay, I don't have time to move on. So we're going to do these practice questions during intervention. I'll video. I need like 15 minutes in there. Will you be here? Okay, so this is the next one we're going to do during intervention. What I want you guys to do for homework is look at the predictions you guys were just attempting. You're doing 1 through 10 for predictions. At least trying them, right? You can't try without maybe missing a couple of them, but 1 through 10 for predictions. And then reactions, reaction, redox, Stoich. I will maybe finish designing them during intervention, but we're going to use some of that problem set. Can you guys find that in your packet? You see the redox Stoich in your packet? How about this? Okay, we're going to do 2 and 3. I want you guys to attempt 1 through 5, but notice the answers on the bottom there, okay? So we're going to do 2 and 3 during intervention. Here's your answers 1 through 5. All right, any questions? All right, I'll see you guys back during intervention. We leave in like a minute.